All right, we're just about to finish section 1.2, and we left off on triangular numbers. And just to remind you of what those are, there is a visual, there it was, a visual picture of the triangular numbers, and then we can assign numerical values based on how many dots are present there. And then we can look for a pattern both in the visual, if we're thinking about it from a younger child standpoint, or in the numerical pattern. And we looked at over here, if you'll remember, number 2, this example here. This is the one that had the triangular numbers here. And we noticed that they had what we called a common second difference. Okay? So there are patterns that don't necessarily follow geometric or arithmetic, but they do follow another type of pattern. So we're going to look at one more type of figurate number, and these aren't the only ones. There are just a couple of them. You're going to see a few more in your book. And what we're going to do is we're going to draw square numbers. So let's see, I need something large enough to work. Let's try that. So the first square number is a single dot, and then I have this one, and then there's this one. Forgive me if they look more rectangular than square. That's okay. And they're not perfect, right? And you're going to forgive me for that too. Do one more. Okay, so let me put some commas between them to differentiate them. This is the first one, second one, third one. That's marking off fourth and fifth. Okay, so they look like squares, or at least they're intended to look like squares with some dots, right? And if we were to count the dots, what pattern do we see show up? Well, the first one's 1. Let's just write the numbers down first, Kaylee. So we have 1, and then we have like, yeah, 4, right? Okay, good. What's the next one? 9. And then 16. And the last one we had is 25. What do you notice about those numbers? They're not multiples of 4. It's okay. They're squared numbers, like they're numbers that are squared. So you probably have seen this in the past, right? That this is like 1 squared, and we have 2 squared, and there's just 3 squared, and 4 squared. Whoops. Let's try that again. And 5 squared, right? So we call them square numbers for a reason. They are numbers that are squared, and their image is a square. And if you think about area from the perspective of multiplication, right? Length times width or base times height, right? When you have them have the same length and the width or the same base and the height, you take that number and you square it. So all of those things are intermingling here. I'd like to show you, though, that they still have the ability, if you didn't recognize this, to do a pattern. Like let's, for instance, just for the sake of argument here, actually, let me do this first. I'm getting ahead of myself. All right, so let's use these numbers, 1, 4, 9, 16, and 25. And we're going to do the subtraction thing, or the addition, like how do I get from one number to the next? So if I go from 1 to 4, I would add 3. 4 to 9, I would add 5, thank you. 9 to 16, 7, and then 16 to 25, 9. And you probably recognize it already. The next one we would add 11. And in fact, it looks almost identical, not exactly, but almost identical to the first one on the screen, right? At least this part of it looks the same, yeah? So that's coming about again. And if you didn't see it and you did it one more time, notice these are all going to be plus what? 2. So once again, they have a common second difference. And imagine if you took 1 dot away from each of these. And I'm just going to subtract the top right-hand corner. I say that I am. Make my eraser just a little bigger. So you don't need to necessarily take yours away. But if this were your image, these wouldn't be square numbers. But we could still count them, right? And we might not recognize very quickly that these are squares in the sense that it's 1, 4, 9, and so forth, right? And in fact, we would have to not have this one here. It would have to not be there at all. We'd have to just start with the second number, by the way. But we would see these numbers in a row, and we would be able to do the first difference and the second difference. The second difference would still be constant. They'd still all be +2s. And this actually would create the sequence that we saw right up here. It would be 3, 8, 15, 24, and then 35. That's what the sequence would be if we just erase the top corner. So there's nothing super special about this image. You can create a figure-it number with whatever image you want, and you can assign a counting strategy for the number of dots that are being used, and you can find patterns in them that way, as well as finding patterns in the image itself, right? So if you're looking at the image that I sort of recreated when I erased that dot, you can see what's happening every time is you're adding sort of a row on the left and a row on the left and the row on the bottom, right? And it just sort of extends and it gets bigger, but that top corner is still missing every time. So there's still a pattern that's going on. All right, this is my last example. This actually really happened. I can't imagine where you were in 2011, but you weren't very old. So in 2011, I was actually here. This was my second year at OBU. And we had just formed what at that time was called the Hurley College of Science and Mathematics. Now it's the Hurley School of Science and Mathematics. But we've had some name changes across campus if you aren't aware, so they've changed some things. But on the board, our dean at that time wrote this number, 3, and then had a decimal point, and then it had a 1, and then a 4, and then a 1, and then a 5. So this was written, and she asked us to write the next 5 terms that come next, like what comes after that, okay? So if you were asked what the next 5 terms are, did I say 5? 2. Why does mine say 5 here? It should say 2. Does yours say 2 everywhere? Yeah? Okay, good. 2 is what I mean. I don't know why mine says 5. Yeah, if you were asked to find the next 2 terms, I would like for you to write down what you believe the next 2 terms would be. Okay? So you're given this, you're said, find the next 2 terms in this number. What would you write down are coming next? Just off the cuff, immediate reaction kind of stuff. Okay. There are 2 possible answers that most people give. I'm going to write both of them on here, and then I want you to tell me which one you wrote down. So sometimes people write this one. So this is where it starts, and they write 1, 6. There's another one that comes about sometimes as well, and it's this one, 9, 2. Okay, who put 1, 6? Okay, so 3 of you put 1, 6. Did the other 3 of you put 9, 2, or did you put something different?
9, 6. Wrong class.
All right, we'll try again. Did anybody put 9, 2? Okay, what did you put, Abby?
9, 6.
You put 9, 6. Okay. Autumn, what did you have?
1, 6.
You did 1, 6. Oh, no, you had your hand raised. Lisa, did you not have yours?
I put 1, 6.
You put 1, 6. You put 1, 6. Kinsey, what did you put? Kaylee? 1, 6. Oh, it's more than you. I just was not looking well then. Mackenzie, what did you put? Okay, so 5 of you put this one. Nobody put 9, 2. So does everybody see how you could put 1, 6 and how that would be reasonable? Okay, good. Abby, where did you get 9, 6?
I don't know.
You weren't sure? Okay. You just thought 9, 6. Okay, that's okay. Does anybody have any idea where 9, 2 might be coming from? Because
the 4 and the 5 and the 1.
Nope. I will give you this hint, perhaps. This might be helpful, but every single math and science professor in the room wrote 9, 2. Not a single person wrote 1, 6.
They added the...
Nope. Nobody added anything.
I don't know.
So in every bit as much as you looked at this and thought, with one exception, obviously it's whatever, perhaps, right? You know, it just seems reasonable that everybody in that room thought 9, 2 was the most reasonable thing, and I thought of nothing else, absolutely. Because 3.141592 is the expansion for pi. And does it make sense that the math and science people would go that direction in their thinking? Probably, right? So the interesting thing, and the reason I point this out, is because what we're doing in this question is called inductive reasoning. And inductive reasoning means making a generalization, like what you think is going to happen based upon what pattern you think you see. And the pattern that Lisa sees may not be the pattern that I see, right? And that's okay. It just means that it doesn't always yield the same solution or the same conclusion depending upon the person and their background. So all the math and science people said 9-2, duh. And most of you said 1-6, what else could it be, right? Like it didn't even register that there would be another choice because our previous exposure, what we're ingrained in most of the time, influences how we see things. So it's a very interesting thing to realize that there may be more than one legitimate generalization to a pattern, and we have to be aware of that when we're asking for pattern completion. So sometimes when a child gives you a pattern completion that's not what you think it is, it might be worth asking, tell me about that. Why did you get that answer? There may be a very valid reason why, and you might have to say, oh, I didn't think about that. So it's just something to be aware of, okay?